Hi, this is Charlie Stanier with online mini lecture 12. To review, in the last lecture, we talked about the aerosol size distribution functions, such as the book's notation, right? N, little n here is the subscript for number, and then the degree symbol would mean this is the base 10 logarithm normalized size distribution function for number, dn d log dp. So this one is dn d log 10 dp. Sorry, dp. We covered the mathematics of them. Please review Chapter 8 of the textbook. We did some practice with reading graphs, approximate integration to get the total number under the curve as the total number concentration of particles, or what fraction of particles are less than a certain size. The best practices for using these are normalization is usually recommended. If you're not going to normalize, you should be using consistent bins because it's difficult to compare size information if it's not normalized and on a different bin basis. Use an x-axis that matches your normalization. If you do so, then you can visually say that the area under the curve is the total quantity without having to do some scaling like 1 over dp or something like that, where dp is particle diameter. And logarithmic axes on the x-axis are preferred for most applications because there are usually features with small particles that show up that way. So in this lecture, we'll talk about the log normal distribution function, which is different from the size distribution function. This is a parameterized fit. Ambient, we'll talk about some typical size distributions that you'd find in nature and show their log normal parameters. And then I'm going to take the opportunity to talk about masks and respirators. Before we get into the log normal distribution function, I wanted to do another example. So this is courtesy of Lindsay Marr again. And what we have here are some distributions, some histograms, right? And so let's figure out what we've got here. It says concentration of airborne SARS-CoV-2 RNA in different aerosol size bins. So you can see, so let's kind of breaking this down, we've got 3 different places: a hospital zone B, hospital zone C, and a medical staff office. Different y-axes. So it's linear y-axis, but this one goes to 60, this one goes to 20, this one goes to 20. The y-axis is RNA copies per cubic meter, right? So they've taken size resolved samples and then done probably PCR or something like that can determine how much SARS coronavirus RNA is present. They used a log axis on the x-axis ranging from 10 nanometers up to probably 10 microns. We'd have to count. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 10 microns. Log scaled. So we've broken it down a lot, but did they normalize? And they did not, right? And you can tell that because this is just concentration. And the units, right, it's not d log dp or copies per log dp. It's not copies per ln, natural log of dp, and it's not copies per micron, which would actually be it'd be copies per cubic meter per micron. So it's not normalized, and so the total is not the area under here. The total, you just add up. You've got 40 in this bin, and maybe 1 in that bin, and maybe 1 in that bin. So this sample has a total of 41 copies, and you can see which sizes they turned out in. This one has 8, 6, so that's 14, 16, maybe 19, 22 copies per cubic meter, and you can see how they're distributed, and then similarly for this room. So I'm saying it's not the area under the curve because if we change this from a logarithmic to a linear scale, we're going to change the area under the curve quite a bit, but we're not changing the underlying data, the number of RNA copies in air. So this is, we can compare these to one another because they use the same bins for all 3 locations. That's probably the same equipment that took all these samples, and so that equipment has some natural bins to it. And we could normalize this if we wanted to compare it to a sample from Europe that used a different equipment or different bins. And there the best approach probably would be to normalize to maybe the base 10 log. So to do that, you would take each bin, you'd say, okay, that's a bin. There's my left bin size, my right bin size, and I would take delta log 10, the right, which looks like maybe 0.2, it's 0.1, 0.2, oh, they marked it, it's 0.25. So delta is this, and that's 0.01. So this is the bin width, and you would take the value, which looks like it's 2, divide by that bin width, and that would be the normalized value of the distribution function. Anyway. All right, so a commonly used fit for distribution information is the log normal distribution function. And so this comes from sort of Gaussian curves, and we say a variable is log normally distributed if its logarithm is normally distributed. And both the base E, natural log, and the base 10 log are in use. It's a 3-parameter fit or a three-parameter representation of the function. We have nt, which is the total number of particles. Sigma g, which is the geometric standard deviation of the distribution. And d over bar p for particle diameter, and this is for the median diameter. So then those are the parameters, and they're natural to use parameters, right? Distribution width, the area under the distribution curve, and the half the particles below, half the particles above. And this also turns out to be the mode. So the base E log normal curve, and I'm going to denote it with a double dagger because we're going to come back to this. So the LNDP. So that's normalized to the natural log distribution function. Its definition is dn dln dp. And then here's the functional representation. So total number of particles, 2 pi square root, natural log of that geometric standard deviation, exp of negative ln dp minus ln dp g over bar squared. All that's over 2 ln squared sigma g. Okay. So my three parameters are here, here, and here. ln sigma g squared is also written as ln squared sigma g, and that is the variance of the distribution. Ln sigma g is the standard deviation. 68% of the area is between ln dpg plus or minus ln sigma g. And then sometimes it's you use the full width at half maximum. Because you can pick this visually. Okay, so here's the maximum. There's half of the maximum, and this is the full width at half maximum. And the full width at half maximum, if this is log normally distributed, is equal to 2.355 ln sigma g. and I said this, but let's write it down. 1/2 of the particles are going to be below dpg. 1/2 the particles above dpg. So that's the base E version of the log normal distribution. And there's also a base 10 version, which I'm going to denote with an X. And in our book, base 10 normalized distribution function is like this. Its definition is dn over d log dp. It's very similar. So total number, 2 pi square root log 10 of the standard deviation, and then our exp term, negative log 10 of dp minus log 10 of dpg squared over 2 log 10 sigma g squared. Then log 10 squared sigma g. It's the same thing as log 10 sigma g squared is the variance. Log 10 sigma g is the standard deviation. And these two are going to be equal, so these are equal when we've got our base E version and our base 10 version. dpg is the same. Total number of particles is the total number of particles. That's the same. Sigma g is the same. And ln of sigma g is equal to 2.303 log 10 sigma g. So that sometimes people will report sigma g, sometimes they'll report the logarithm of it. And so you just have to watch for that. Here's an example of some log normal distributions. So these all have the same total number of particles. So the same area under each of the curves. They all have the same median diameter of 100 nanometers or 0.1 micron. You can see half are above, half are below. And then we've got a wide distribution, somewhat narrower, even narrower. And then these are the base 10 logs of those three values. So I'm just going to show that before I said that the half width, full height at half maximum is related to the variance. So we're going to show that for the narrow distribution. So the narrow distribution, 100 nanometer mode, 1,000 particles, and its sigma g was 1.5, log 10 of sigma g was basically 0.18. Our formula said the full width at half maximum would be 2.355 times the log 10 of sigma g, or 0.42. Right? And then what we've done is we've marked, that's halfway up. There's x1 and x2. x1 is 0.06 microns. x2 is 0.169 microns. And the difference of their logarithms is 0.41, as expected from the formula. So how do you've got a distribution. You've got some data. That doesn't look like the autofocus is working well. Get it that way. So I've reached sort of the limits of the document camera, but these dots here represent the data. Right, and what we've done is written a MATLAB code that fits through the data and finds the best log normal curve. So there's kind of two approaches. You could try to get the total number of particles by adding up all your heights here from your data, estimate some sort of variance. It's hard to do the full width at half max because the data cuts off before it gets down halfway to the full height. And then you need the third parameter is the mode. And so you could come up with some sort of approximate estimate of the peak here. Right? With those three parameters, you've got it determined. Or you can take a numerical, sort of minimize the least squares error and try to optimize those three parameters. So there's a MATLAB program that is used in our group to do this. This is the one log normal fit. This is adding together 2 log normals. This is adding together 3 log normals. And with 4 log normals, we're basically going through, all the data. We've got one very wide one, a narrow, 2 narrow ones, etc. So this is not published. It's available if anybody needs it for their research. You can have it. Just contact me. There are 2 published sets of codes where you can download the program. And here are those citations, and you've got this in the slide deck. So this is a Finnish group that does a lot of fitting of size distributions, and I'm not familiar with this group. But I think Tom Peters' group over in public health made some products that were based on this method. All right. So this is a summary of some material from the book on outdoor or ambient size distributions. And it's common to use 3 log normal modes. For the volume distribution. Sometimes also the number, but here's typical ambient volume distribution. So NV base 10, so there's 0.1 micron, 1 micron, and these get divided into 3 modes. One that we call the coarse mode, one that's called the accumulation mode, and then it depends on what text or paper you're looking at and how small, but there's a nuclei mode or an Aitken mode. They're not quite the same, but they refer to usually the smallest mode of a 3-mode distribution. They're fresh particles that just nucleated from gas to particle processes. The accumulation mode is called the accumulation mode because it has a long atmospheric lifetime. It's not efficiently removed by gravitational settling, rain out of particles. Coarse mode particles have a short lifetime because of gravitational settling and removal by rain. Nuclei mode particles have a short atmospheric lifetime. They're removed through coagulation. They will bump into larger particles, stick, and be lost. So they grow the larger particles. A lot of collisions between nuclei and accumulation mode particles that lead to just slightly bigger accumulation mode particles. And when you add these together, you get an overall size distribution that looks like that. And because we built this from 3 log normals, we can represent it with 9 parameters. So there's a 9-parameter fit here. And it's 3 for each mode. And that's going to be total volume. Well, we're going to switch back to the number representation. The number in each mode, the mean size of each mode, and then a standard deviation of each mode. So this is going to look very much like our old log 10 log normal distribution function, but we're going to add together 3. The coarse mode is going to be composed of mechanically generated particles. Such as dust, fly ash, which is ash that from combustion that goes up the stack and flies away rather than being collected in pollution control devices or falling into the bottom of the combustion zone. Brake dust, sea salt, tire wear particles, and the nuclei or Aitken mode and the accumulation mode are mainly once we add these together, it's going to be this is going to be primary combustion, so smoke, and then gas to particle secondary material. Some terminology you might run into: TSP, total suspended particulate. PM10 would be the mass with diameter below 10 microns. And PM 2.5 is going to be the mass with diameter below 2.5 micron. Now, in practice, these get measured with real devices, and those devices don't have sharp cutoffs at 2.5 microns. They have fairly sharp, but they'll sample, all 2 micron particles, most 2.4 micron particles, about half of the 2.5 micron particles, and then hopefully the cutoff sharp enough that they don't sample any. So it's something like this, where this would be 2.5 and this would be your collection efficiency. And this would be 100%, 50%. A lot of effort goes into designing sharp cut samplers. And then we said there's many different diameters, and most of these work on some sort of aerodynamic inertial collection. And so this diameter is really the aerodynamic diameter. Oh, I've been bad. I haven't been putting page numbers on. So let's see. It's 33, 34, 35. And then we've got some different locations: polluted urban, polluted rural, remote, implying not polluted, continental, so overland, desert, with no people, right? Not Phoenix, marine, remote, the free troposphere in a remote location, and then polar locations without humans nearby, so clean polar. And we can characterize these by their particle number and by their PM10. And we usually use units of inverse centimeter cubed, so number per cubic centimeter of air. And here we usually use micrograms of mass per cubic meter of air. Typical values might be 100,000. It's going down as cars get cleaner. And this would be 100 to 300 for a very polluted city. Then we get to about 10,000 here. Again, this is going down as sulfur emissions are going down. 20 to 40. 2,000. 1,000. 200. Maybe 200 for a free troposphere. And then in the absence of pollution influence from either local sources or long-distance sources, a polar site might have 30 particles per cubic centimeter. And then the book has a lot of typical size distributions. So let's start with the urban one. So let's see if we can interpret this. This is n sub n e. So this is the natural log normalized size distribution function. Sizes running from 3, 4, 5, 6, 7, 8, 9. Yeah, probably 3 to 10. 10 to 100 nanometers, 1 micron, 10 microns. So here's our coarse mode. There's our accumulation mode. And the nuclei mode is so small it doesn't show up in the particle volume. This has got cut off. This is surface area, volume, and number. So urban location, common particle number might be 10 to 20 nanometers. The surface area mode might be around 200 nanometers. And then the volume will often be bimodal, one for the coarse particles from dust and tire wear and brake wear, and then one for the accumulation mode with the combustion exhaust and the secondary processes. So total number of particles can be determined by integrating under this curve. And so this is 1 decade. The average height is about there. So the area of a box like this, just draw it. So I'm saying this box has about the same area as the actual curve in that size range. And then we've got a significant number of particles here that might be something like that. And if we call this 1 decade and 1 decade, even though this one's a little short of 1 decade, this one would contribute 10 to the 5 times 1, and this one would contribute 0.4 10 to the 5 times 1 for its width. And so in total, that would be 1.4 times 10 to the 5, or 140,000 number per cubic centimeter. But I made a mistake, because this is the base E distribution function, and I treated it like it was the base 10 distribution function. So my mistake is these ones, because log 100, log base 10, 100 nanometers minus log base 10 of 10 nanometers is 1, but I need to be doing the natural log. And so I believe that's going to be a bigger value by a factor of 2.3, but we'll cross that out. The overall height, though, you see is 210 to the 5, right? So we go to a less polluted location. The height is no longer 210 to the 5. It's now only 7,000, so it's much, much fewer particles. So this is a typical rural continental: number, surface area, volume. Similar shapes, but they're saying, oh, this rural continental is enhanced in the coarse particles because of all the dust. And then the third one shown here, and the book has more, desert, right? So the number distribution height was 210 to the 5 for urban, was 7,000 for rural continental, and now we're down to 300. There are not that many particles in the desert, but the ones that are there are typically bigger. So you see our volume distribution is all out here in the large particles. And so this is just blowing desert dust. And it would extend to even larger grains of dust that would have very short lifetime. So those are some typical distributions, and these can be represented by 9 parameters, 3 for each mode. And so modelers like them because if you need a typical distribution, you can go get a value, or if you have some experimental data, but you just need sort of a monthly average of it, you can fit some log normal modes, represent it by just a few numbers, and put it in a model that way. So I'm going to finish up because of the coronavirus situation and how that ties into aerosol distributions and their sizes with masks. And you have the PDF of this, but so surgical masks versus respirators. And you can see their purposes. These are designed to filter out particles. And there's different types depending on how tight the pore size is. That's going to determine what kind of particles get through. Lindsay Marr provided us some nice tips. This little metal band here at the top goes over your nose, not over your chin. And this helps get the fit right. So there are 3 things that must be done with respirators. Number 1, you need to wear it during the exposure. So if it's in your car when you need it, that's not going to help. If it's on your arm because you store it there, it's not going to help. Number 2, must fit well. So anywhere where there's an air gap, the air is going to go there with the particles, and it's not going to do its job. And then it must capture the particles in the filter media. And so an N95 is designed to block 95% of particles in all size ranges. Or stated more correctly, there's going to be a size that is the most challenging for the filter media, and even at that size, it should filter out 95 if we're going to call it an N95. The mechanisms that these masks work on are, any filter, the house filter in your furnace or something like that. Impaction, right, which is particles. So here's streamlines. So here's a fixed fiber in the mask, right, and the airflow is being sucked across that fiber. And there are three things that can happen that lead to a particle being collected on the fiber. One is inertial impaction. It has so much inertia that even though the air streamline bends around the fiber, the particle keeps going straight and impacts. Number two, interception, is that the streamline and the particle bend around, but because of the particle's size, it gets caught on the edge of the fiber. And diffusional collection. So very small particles have Brownian motion. Not as much as gases, but they have some, right? And so small particles are going to follow the average gas streamlines, but they're going to be moving around, and some of those movements might impact them onto the fiber. Right? So big particles get collected well because of impaction. Really small particles get collected well because of diffusion. And as this figure shows, the accumulation mode, right? Particles are the ones that aren't collected by any of the mechanisms very well. So this is particle size versus collection efficiency, right? With diffusion shown here, effective for below 20 nanometers. Sedimentation is just particles falling out of air. Impaction is them impacting on the fiber. Interception here, and then we can add together that, and get a total collection. Right? And so this example has the weakest collection at around 150 nanometers, and at that size its collection efficiency is 75%. Collection efficiency is affected by relative humidity, charge of the filter media, charge of the particles, the amount of stuff that's already collected on the mass, so it's not as simple as shown here. And I'll stop there.